the organizers for giving me the opportunity to present my work here. This work is what I did for my PhD thesis, and I want to thank my advisor, Mike Anderson, as well. All right, so let me start by telling you what a conformally compact manifold is. So you take the interior of a manifold with boundary, okay? And let me first tell you what a defining function is. So a defining function is a non-negative function rho on M bar with the pre-image of 0 is actually the boundary. And we also need that regularity condition over there, d rho not 0 on the boundary. And we say that a complete Riemannian metric G on M is said to be conformally compact if there is a defining function rho on M bar such that the metric G bar equals rho square G extends to the metric, extends to the boundary. Okay, we're gonna see an example in a minute. All right. So, and what is the conformal infinity? The conformal infinity is the restriction, is the conformal class of the restriction of the metric G bar to the boundary. Okay. So, like, you don't have a unique defining function. Okay. But if you take another defining function, rho 0, for example, you get another metric on the boundary, but the conformal class is the same as the other one. So the conformal class is well defined. Okay, so we call this conformal class the conformal infinity. Okay, let me give an example. So it's the simplest possible example. You take M to be the open ball, and the metric G is that metric over there. Okay, it's just a function times the Euclidean metric. And in this case, your defining function is the function rho given by 1 minus x squared over 2. Okay? And the metric G bar, which is, remember, G bar is rho square G, is going to be the flat metric on the disk, on the closed unit ball. Okay? So in this case, what you get for the conformal infinity is the conformal class of the round metric on the sphere. All right? Okay, so I'm interested in conformally compact metrics which are also Einstein. Okay? So I'm going to normalize my metrics such that the Ricci tensor is minus n times g. The dimension of my manifold is n plus 1. Okay? All right, so it's a not so bad computation to show that with this normalization, the sectional curvature converges to -1 as you approach the boundary. Okay? So these metrics, the conformally compact Einstein metrics, they generalize the Poincare model for the hyperbolic space. All right, so people also call these metrics Poincare Einstein or asymptotically hyperbolic. I like the Poincare Einstein name better, so I'm going to stick to it. Okay, so we're going to do analysis on these spaces. So we need nice function spaces. So in this case, we're going to use holder spaces. Okay, so we have the the M alpha holder space of metrics on the boundary, and like some technical remark is that the topology is the C M alpha prime topology for some alpha prime less than alpha. This is just so that when you take bounded sequences, they have convergent subsequences. Okay. So E M alpha is going to be the space of Poincare Einstein metrics. okay, such that they have a CM alpha compactification. Okay. And again, I put the CM alpha prime topology for some alpha prime less than alpha. Okay. So I'm not distinguishing metrics which are which change just by a diffeomorphism. Okay. So I'm going to consider the moduli space E. Okay, there's curly E, which is the quotient of EM alpha by the set of diffeomorphisms that fix the boundary. All right? Okay, so you have this natural map. So this is called the Dirichlet boundary map, and what it does is it takes a Poincaré Einstein metric on the manifold M and sends to our conformal class on the boundary. So, for example, if you have the hyperbolic metric on the ball, here's the flat metric, okay? So pi of this metric is just the conformal class of the standard metric on the sphere, okay? All right, this is round metric. Round metric on Sn. All right. Okay, and I'm also going to need the space of CM alpha symmetric bilinear forms on M. All right, so you have these weighted Holder spaces. Like, instead of going through the definition, let me just tell you that they are Holder spaces, but they have some decay, okay, as you approach the boundary. And the important thing is that if you take if you take delta equals 2 on the definition, you get this property that two metrics G tilde and G that differ only by an element in the space, in this weighted Holder space, they're going to have the same conformal infinity. Okay? So the idea is that I want to find an Einstein metric on my space. So I take an approximate solution to the Einstein equation, and I'm going to change the solution, this approximate solution, by an element in this weighted Holder space to get an Einstein metric. So the conformal infinity is not going to change. It's going to be the same. Okay? All right, so what is the Dirichlet problem? I give you the topological data, M, and the boundary of M, and I also give you a conformal class on the boundary, and I ask if there is an Einstein metric such that the conformal infinity is that conformal class. Okay, so it's a very simple problem to state. And so, like, surjectivity of this problem, surjectivity of the boundary map corresponds to existence, and injectivity corresponds to uniqueness. And there are cases for which this map pi is not unique. The first example was the one found by Hawking and Page in 1982. And these metrics are called ADS Schwarzschild. Okay. All right, so we're going to see more about the injectivity later on. But regarding the surjectivity, there is this result of Anderson that it builds on work of Graham and Lee and Bicor. Okay. So let me tell you what Graham Lee did first. So you have the round metric, and for the round metric you have the hyperbolic metric such. Okay, so the conformal infinity of the hyperbolic metric is the round metric. So what they did was they took conformal classes close to this one. Okay, so it's a perturbation result, and they showed that if the conformal class is close enough to this one, you can now find a metric close to the hyperbolic one, such that pi of that metric is that conformal class. Okay, so Biquat extended this result, and then Anderson proved this more general one. So there is this. Sorry, I should put M bar here. Okay, not M. So there is this topological condition here. It's just saying that the loops that are non-trivial in M, they come from non-trivial loops on the boundary. Okay. So he showed that if this space is non-empty, then it in fact has to be a Banach manifold. And moreover, the boundary map, the map pi, is a Fredholm map of index 0. Okay. So in particular, if you have if the kernel of the differential is 0, you get some local surjectivity. All right. Okay. So that's Anderson's result. This was done this was published this year, but was done I think 2 years ago. So let me talk a little bit about orbifolds. My orbifolds are going to be very simple. They are not the most general kinds of orbifolds. So for me, an orbifold is just a space that, except for finitely many points, this space is a manifold. But you have some points that are the singular points that the space is not a manifold there, but it's still very simple. You can always pass to a cover. Okay. So that's what it's saying here. So these points, which are the singular points, they have neighborhoods homeomorphic to a cone on a spherical space form. So you can pass to a cover and work on this cover. Okay. So the same function spaces that we defined for manifolds, the CM alpha, the Holder spaces, you use this cover, and you can easily define these spaces for these simple orbifolds as well. And I'm going to call what I called before EM alpha and curly E M alpha, I'm going to call F and curly F. So you also have a boundary map pi F. Okay. All right. So let me tell you what a smooth resolution is. So you have an orbifold V. So a resolution of this orbifold is a pair M pi, okay, where pi is a continuous map from M to V, such that when I restrict to the per-image of the regular points, this map pi is a diffeomorphism. Okay, and also the pre-image of each singular point is a two-dimensional CW complex. Okay. All right. There is also the notion of orbifold singular Einstein metric on a smooth manifold. So this is just the pullback of an Einstein metric on an orbifold. Okay, an Einstein metric on an orbifold is just an Einstein metric on the points that are not singular. Okay. So orbifold singular Einstein metric on a manifold is the pullback of an Einstein metric on an orbifold by a resolution. I map pi like that. Okay. All right. So Anderson has this approach to prove surjectivity of the boundary map, and in his approach, it's very important to see if this map pi is a proper map. Okay, if it takes if pre-image of compact sets are compact. So if it's not proper, it's important to understand like what kind of degeneration can occur. Okay. So what he did in 2008 was he proved that if you take a sequence of metrics of conformally compact Einstein metrics on a 4 manifold, such that the conformal infinities are in a compact set gamma, then like at most three things can happen. Either you have convergence, and great, okay. You can have orbifold degeneration, okay. So your sequence, some subsequences conversion to a metric with orbifold singularities, or you have formation of cusps. Okay. So the problem that he gave to me for my PhD was to try to understand these orbifold degenerations a little better. Okay, they are not well understood. All right, so I'm just writing down 1, 2, 3 again in more detail. Okay, so I mean I'm really interested in 2 here. So what does it mean to for my sequence to have to degenerate to an orbifold metric? It means exactly this. Okay, it model diffeomorphisms. It converts to a limit Poincare Einstein orbifold singular metric H on M. Okay, and outside the singular points, the convergence is good. Okay. All right, and you also have Gromov-Hausdorff convergence. Okay. All right, so. What I do here is just to basically repeat like the number 2 here, and then take it as my definition of orbifold degeneration. Okay. So a sequence GI of CM alpha conformally compact matrix on M degenerates to a CM alpha conformally compact matrix H on V. So V is my orbifold. If the following hold: the first, you have Gromov-Hausdorff convergence. And second, there is a resolution pi in a defining function rho satisfying the following. For n open subset U of M bar with U contained in the pre-image of the regular set, the sequence of compactified matrix G bar equals rho squared GI converges in CM alpha U. Okay, to this metric here. Okay. All right. So, there is at least one. I mean, like it in fact it can happen that a sequence of Poincare Einstein matrix degenerates to an orbifold. So you have this example here of the Taub-bolt, the ADS Taub-bolt family on the tangent band of the two-sphere. All right. In fact, it's a curve of matrix, not only a sequence. And once you have this, you can use a construction due to Mazel and Paccard. Okay. So what they do is, so the paper is called Masquet Combinations. Masquet combinations of Poincaré Einstein matrix. Einstein. And what they do is they take two of these spaces and they do a boundary connect sum construction. So it's a gluing theorem. Okay. So they start with two Poincaré Einstein matrix and they construct a Poincaré Einstein matrix on this new space here. All right, so it gives like lots and lots of examples of matrix. So once you have this, okay, so you have a specific example here, which is the ADS Taub-bolt, and then you can do the same construction that they did, and you get other examples of Orbifold degeneration. But beside these two kinds of examples, people don't know if there are more. Okay, so it would be an interesting problem to like find examples of degenerations with different topologies than these ones. It's probably hard, but I don't know. All right, so let me talk about the Einstein operator now. So, as people already mentioned here, you have this operator, and it's not elliptic because it doesn't change with it's invariant by diffeomorphisms. So what you do is you choose a gauge. So in this case, a nice gauge to choose is the Bianchi gauge. So it's just okay. So you have a metric G tilde here, and let's say you want to find a metric G close to G tilde that is an Einstein metric. Okay, so you have the Einstein equation here, but you also impose this gauge condition. Okay, and now you have this system, and it's elliptic now, and so you're good. But what people do is, instead of working with these two equations, they work with this single equation here, phi. Okay, so this delta star is the dual, the formal dual. Okay, and there is a result by Biquois that if phi is 0, then these two equations are actually 0. So in this case that we are working, at least. All right, so if you linearize this operator phi, what you get is this L, okay? And I mean, I think it's a complicated expression, but people think it's simple. And okay, so you have this L over there. Okay, so I'm going to say that the Einstein metric G is non-degenerate. So I'm overusing the word non-degenerate here, like, okay, but so I'm going to say that it's non-degenerate if the kernel of the Fredholm operator LG is trivial. If the kernel is not trivial, I'll say that the Einstein metric G is degenerate. Okay, so Anderson made this conjecture, and later on we're going to see that the conjecture makes a lot of sense. Okay, so that he conjectured that whenever orbifold degeneration occurs, then the limit orbifold metric has to be degenerate as well. So has to be degenerate. Okay, so if you have a sequence of Einstein metrics convergent to an orbifold, this orbifold has to have a kernel. Okay. So the first thing that I did was I did the computation for the Taub-bolt, the ADS Taub-bolt family, and I found out that the answer is no. Okay, it's surprising actually. Okay, so here's a explicit expression for the Taub-bolt metric. So it's a metric on TS2, the tangent bundle of the two-sphere. Okay, so here I have coordinates r, tau, theta, and phi. So theta and phi are spherical coordinates, and r and tau are polar coordinates on the fiber. So I mean, you have this huge expression, and what happens here is here s is greater than 1 always. But what happens is that when as s goes to 1, you have an orbifold, and the expression simplifies a lot. Okay, so you have a huge cancellation, and you get this orbifold metric here, and the orbifold is the cone RP3. Okay, it's just okay. It's so what has happened is that the geometrically is that the base of the bundle is being crushed. Okay, so in the limit you get the cone, and the metric has this, I mean, still complicated but not so complicated expression. Okay, and then I did a computation. Of course, I made several mistakes, and I had to do it like at least 3 times. But I computed the curvatures. Okay, I took this frame, and you have co-frame, connection forms, curvature forms, and then finally I found the curvatures for this particular frame that I took. And it's important that it was a nice frame, because it made some things very much easier later on. So okay, so you have so they're all negative here, but I want to show that they are negative in general. Okay, so I took a plane, okay, generated by V and W, and if you compute the curvature tensor, you get this quadratic expression here. And the only thing you have to show is that this determinant here, this how do you call it, discriminant, right, is positive. Okay, and it happens. Okay, so if you plug in these values there, it happens. So what you find is that all the curvatures are negative. Okay, So, okay, so the sectional curvature is minus. For me, the way I chose my notation is minus this. Okay, so all the curvatures are negative, and then you can use a result by Koizu that that operator L has no kernel. Okay, so that gives a negative answer for the conjecture of Anderson. All right, so that was the first result. Just a huge computation, but it's surprising. It's okay. So let me do some setup here. So I'm gonna take an orbifold metric H. Okay, and gamma is the conformal infinity of H. Okay, so I have this neighborhood Z inside the set of conformally compact Einstein matrix. Okay, and I have this neighborhood W inside the set of conformal infinities. Okay, C M alpha. Okay, so I have the conformal class gamma. I have an orbifold metric here with gamma as conformal infinity. Okay, and I suppose that there is a curve of Einstein matrix on M. Okay, a curve of Einstein matrix on M converging to H. And not only this, but I also suppose that for okay, so the way I'm setting things up, this map is a diffeomorphism. So if you take a conformal class here, I call H theta the only orbifold metric that has that conformal infinity. So I'm also supposing that I can take the Z that all these metrics here can be approximated by orbifold all these orbifold metrics can be approximated by smooth Einstein matrix. Okay. All right. So this is my setup, so the second result that I got was this one. So with some hypothesis, you have that injectivity fails. Okay. So if there is T0 in 0, 1 such that GT, okay, this GT here is non-degenerate, okay, for each T in 0 T0, then you can find disjoint curves, okay, with the same conformal infinity. Okay, so in particular, the boundary map is not injective. And the proof is actually very simple. Okay, so once you do it for 1, you can do for k. So the corollary here is just the same result, but for k curves. So the proof is actually very simple. So you take your, you have your initial curve here, GT gamma, converging to the orbifold metric H gamma, and at some point, T1, the conformal infinity of the metric GT is going to be inside W. Okay? So since I'm supposing that these metrics are non-degenerate, you actually have neighborhoods here, y, t1, okay? And so yt1 is a neighborhood in that set E, okay? And you have neighborhoods yt1 and xt1 such that the boundary map here is a diffeomorphism. All right? Okay. So you have the theta here, which is the conformal infinity of this metric. And then you're going to have an h theta, just like I drew on the board. And remember, I'm assuming that there is a curve converging to this h theta. Okay? All right. So at some point, the conformal infinities of this curve are going to be inside this neighborhood xt1. But remember, there is a diffeomorphism. The map pi, the boundary map, is a diffeomorphism between y and x. So you find another curve here, okay, inside y, such that the conformal infinities of this curve and of this curve, they coincide here, okay? And these two curves, I call this one G1 and this one G2, these two curves, they are different because since you have orbifold degeneration here, the holder norm has to go to infinity, okay? And here it stays bounded. All right. So it's simple. So that was the first result. Okay. In this case, you don't have the activity. So since you have a really strange thing here, if you think about this corollary, it's really strange what is happening here. I made this conjecture, and I thought I had this conjecture for like a month. It was a really happy month for me, but then I realized there was a gap. The conjecture is that whenever you have a curve or Poincare Einstein matrix degenerate into an orbifold, converging to an orbifold metric, you can always find a sequence converging to zero such that GTI is degenerate. So the kernel of the linearized Einstein operator is non-trivial. Okay, so I would like to see someone I'd like someone to do that. I really think it's true. So okay, so for the next two results, I don't need that condition anymore. That sorry. This one here. Okay, that every conformal infinity, for every conformal infinity, you have a curve converging to the metric h theta. Okay, but I'll need another condition. So for the next two results, suppose that the orbifold metric H is a non-degenerate Poincare Einstein metric on the orbifold V, such that there is a curve converging to H. Okay, but it's just to this one. I don't need for the other ones. So here there is this not so natural condition, and later on you're going to understand why it's there. So I consider this map psi. Remember that phi is the Einstein operator with the with the Bianchi gauge, with that gauge condition. So I consider this psi, which is basically the phi, okay? And remember that the linearization of 2 times phi is, I called L. Okay, so there's this condition here that, I mean, my advisor liked it. I confess he didn't like it very much. That let me read the whole thing. So suppose there is a T0 in 0, 1 such that GT is non-degenerate. Okay, so there is no kernel for T in this interval. And I suppose there is this constant mu such that the derivative of psi is Lipschitz with constant mu, okay, for each t. So it's the same constant for each t, okay? And suppose also that this set here, the norm of the inverse of the operator is that the conclusion is that this set is unbounded. So if you suppose that it's bounded, you get a contradiction. Okay. All right. So I have an hour. Yeah. Right. Yeah. So I have. Okay. I'm good. Okay. So there is this lemma. I think it's easier if I just show you the picture. The lemma is saying that. I'm going to show you the picture in a minute. The lemma is saying that if you have neighborhoods yt and xt of gt such that you have a diffeomorphism, this neighborhood xt cannot contain this set here, which is the set of conformal infinities of the curve. Okay, so let me show you the picture. So this situation here cannot happen. Here you have the curve converging to the orbifold, and you have the conformal infinities of the curve here. So this yt and xt are set such that the boundary map is a diffeomorphism. So it cannot happen that this set contains the curve here of conformal infinities. Okay, and it's not. I mean, it's not hard to prove. It's just so again, you use the diffeomorphism to find. So you have this initial curve. So this curve, the conformal gives you a curve here of conformal infinities, and then you can lift this curve to this neighborhood here. And these two curves, they have to be different because this one, the Holder norm is converging to infinity. And this one here, you have bounded Holder norm. Okay. So here's the lemma. And what the way you prove the theorem is just by showing that. Let me put here on the theorem again. The way you prove the theorem is just by showing that you can pick these neighborhoods xt, these neighborhoods xt and yt, xt, such that the side of this neighborhood is uniform. Okay, so as t goes to 0, it stays. It doesn't shrink too much. So at some point, it's going to contain you're gonna be exactly in this situation here of the lemma. So, and the way you do this is just by using the contraction mapping principle or Newton's method. I mean, which is basically the same thing. Okay. so you construct an approximate metric G tilde, okay? And the way you construct this is by chopping. So you have your Orbifold metric here. Here should be, yeah, no, that's right. You have your Orbifold metric, h theta, and you have your curve here, and you chop these metrics, and you construct an approximate solution for the Einstein equations by pasting those together. Okay? And then, so you want to find an Einstein metric, so you're gonna perturb this approximate solution by an element in a weighted Holder space here. Okay? So this corresponds to solve this fixed point, to find a fixed point of this map here. Okay, so you have a bound on the you're supposing this operator here is bounded, and also you have that condition that I said I didn't like, that Lipschitz condition, and that condition is exactly what you need when you go to the proof of the inverse function theorem. If you have that condition, you can choose the neighborhoods to have a uniform size. Okay, so that's why that condition is there. Okay, so once you have uniform size for your neighborhoods, okay, you can, at some point this is going to happen. Okay, so the neighborhood xt is going to contain the curve of conformal infinity here, and this cannot happen by the lemma. Okay. All right. So, and that's what I just said here. So you can take this xt uniform. So look that this last theorem, that it kind of justifies the conjecture made by Anderson. So the inverse of this operator has to do with the first eigenvalue. So if this thing is going to infinity, you expect the first eigenvalue to go to 0. So you expect the Orbifold metric to have a kernel. Okay, but it's not true. All right, so it's surprising. All right, so thank you.